All right, let's look at the second part of example 2. Determine whether each function is continuous with a given value. Same thing. That symbol didn't come off very well. Maybe it does in my Notability copy. This is supposed to be the greatest integer function. So g of x is equal to the greatest integer function at x is equal to 3. Okay, then. Let's see what it looks like over here. Oh, yeah, it looks way better. All right, so the very first thing that I need to do is figure out whether or not g of 3 is defined. And so the way that I do greatest integer, I ask myself this. What is, maybe I should write this down. What is the greatest integer that is less than, less than, not less that, and I did it again, less than or equal to, in this case, 3. So what's the greatest integer, the biggest integer that is less than or equal to, oh, wait a minute, yeah, I did say that, or equal to 3? Well, it's 3. So it's defined. So g of 3 is defined. Okay, that was unhelpful. So now let's try the limit. The limit as x approaches 3, greatest integer function of, x, is equal to, well, you know, our first step is usually a direct substitution here. So if I plug in a 3, if I plug in a 3, greatest integer less than or equal to 3 is 3, but it's unhelpful because I really don't know what's happening on both sides of 3. So here's an instance where I need to do the left-right. I need to break this up into seeing what's happening on the left side, see what's happening on the right side in order to conclude what's happening on both sides at 3. So I'm going to write the limit as x approaches 3 from the left. There we go, greatest integer function. So here's the way I think of it. A number that's a little bit smaller than 3. So I'm just kind of thinking of a number like, how about 2.9? And then I want to ask this question here with 2.9 in it. What is the greatest integer that is less than or equal to 2.9? It's not 3, it's 2. Because, like 3 is bigger than that number, we want the greatest integer that is smaller than or equal to that number, so it's just the number 2. All right, then I'm already having a bad feeling about this. The limit as x approaches 3 from the right-hand side, boop, ba-doop, ba-doop. So on this time, I'm trying to think of a number that's just a little bit bigger than 3. How about 3.1? That's a little bit bigger than 3. So what is, I'm going to go back up over here, change this 3 to a 3.1. What is the greatest integer that is less than or equal to 3.1? Well, 3.1, it's not going to be up to 4. It doesn't round up to 4. No, in no kind of way. It would round down to, just like before, 3. Okay? So an interesting thing about greatest integer functions is this. This we would do like in terms of rounding, because it kind of is, but it's always rounding down. No matter what, it's always rounding down. It's sometimes called the floor function here. And 2.9, I usually think of it as a number that's going to round up to, say, 3, but you can see that here this limit is actually 2. It's going to spit out the number 2, and this one a 3, even though, yeah, that does make sense that it would round down to a 3. What can I conclude from this? I can conclude that the limit as x approaches 3 of the greatest integer function of x, d and e. And why is that? It's got different left-right behavior due to different left-right behavior. Therefore, hey, I'm going to do these 3 fancy dots here for therefore. F of x, is it f of x? It's not, it's g of x. G of x is not continuous. Observe how I underline that. It's super important. Continuous at x is equal to 3. Let's look at the graph for that one back over here. Badoom, and you can see, yeah, obviously if I were to look at specifically at 3, it's not continuous on that graph right there. It would be continuous anywhere in between. If I had picked anything in between these two endpoints here, it'd be fine, but I picked it at the endpoint where it's not continuous. This is a type of discontinuity that's called a jump discontinuity, because I have to jump from, say, one of the points to get up to the next part of the graph. All right, let's look at the fourth and final one here. G of x is equal to, oh, we've got some sort of piecewise function. 1 over x squared if x is equal to 0. What the heck? X is not equal to 0. And 1 when x is equal to 0. Oh, okay, I see. And then we're trying to determine whether it's continuous at x equals 0. That's totally confusing. All right, anyway, who typed it up? I did. I have nobody to blame but myself. All right, well, I've got a piecewise function. When you have a piecewise function, as far as determining whether your function exists at that point, whether it's defined, you look for where the equal sign is. So we want to see what is g of 0. So g of 0, like it tells me I got to use this bottom portion right here. It's going to be 1. Sometimes it's not an equal sign. Sometimes it's like x is less than or equal to 0. So then I would use that portion in order to evaluate my function there, right? All right, let me get rid of this just in case somebody comes in and is confused by that, like right in the middle of the video. Anyway, so this one's equal to 1, which is defined. In other words, our first item in that checklist, it's good, it's golden. All right, so the next one is to check the limit. So the limit as x approaches 0 of 1 over x squared. Direct substitution, I put 0 in there, I get 1 over 0, and I'm supposed to associate that with plus or minus infinity. Well, this one I know is positive infinity. Just take a look at the function there that I'm evaluating it at. I've got an x squared down here. My numbers are always positive on both the left side and the right side of 0. So even in the negative ones, when I square, it's going to be positive. The right side, it's going to be positive. So no matter what, this one is actually equal to infinity. And remember, that means D and E. It means that it does not exist. So since the limit does not exist, I can stop right here and say that our function is not continuous. Therefore, g of x is not continuous. Oh, wait, underline. At x is equal to 0. Let's take a look at the graph on this one, shall we? We shall. Here we go. And you can see that it looks sort of like, I don't know, a volcano or something. We have a vertical asymptote. It's just that somebody, for some strange reason, dropped a point right into the middle of the volcano and it just got stuck right there, like in the volcano's throat, right there at 1. Anyway, it doesn't matter that that point's defined there. The limit doesn't exist there, therefore it's not continuous at that particular point. So here is our third and final discontinuity, and this one is an infinite discontinuity. Infinite discontinuity just means that you have a vertical asymptote. And this is terminology that you'll absolutely see and probably use on your AP Calculus exam. So let's write something up for these types of discontinuity. If a function f is defined on an open interval, except possibly at a, remember open intervals like from negative infinity to positive infinity, from negative 1 to positive 1 with parentheses around it, and f is not continuous at x equals a, then f has a discontinuity at a. And here are the types. So here's the first one. It's removable. It's a pointed discontinuity. This one, the limit is still going to exist there. Okay, and then we have two non-removable discontinuities. The first one is a jump discontinuity. The limit is not going to exist at that particular point due to differing left-right behaviors. And then we have our infinite discontinuity, and the limit is not going to exist at that particular point due to unbounded behavior. So these last two, the jump and the infinite discontinuity, are examples of non-removable discontinuities. Their limits are not going to exist, but the removable one is.